Welcome to Module 11. We're going to be talking about residual properties in this lesson. So our goal here will be that we can define what a departure function or a residual property is. Now, I've shown enthalpy as an example, but there are two different languages that are used alternatively. So departure functions or residual properties. We're going to be able to calculate these departure functions or residual properties for pure substances using equations of state. And then we will see how these can be used with a hypothetical calculation path to solve first law and second law problems for real fluids. So what is a departure function? A departure function is simply the difference between the property of a real fluid at a specified temperature and pressure and that same substance if it were an ideal gas at the same temperature and pressure. Now Smith, Van Ness, and Abbott call these residual properties, but departure functions are a little bit more common these days. Most of the time when we're talking about a departure function, we're going to be doing it for enthalpy or entropy, but it really could be defined for any thermodynamic property. So the idea is that this departure or residual is how different it is from the ideal gas. So it's the actual property minus the ideal gas property for that same thermodynamic temperature and pressure or whatever state is defined. So why would we do this? For any change in state and variables, a calculation can be done for any continuous path. It doesn't have to be physically possible. So if I wanted to go from state 1 to state 2 for some real fluid, I could certainly do the calculation along this actual process path. But it might be easier if I said, well, what happened if I took this and turned it into an ideal gas, changed just temperature, just pressure as an ideal gas, and then bring it at this final temperature and pressure back to being a real fluid. So although I couldn't physically do this, this does form a continuous path with the same starting and stopping points. So this is the path that is typically used. You start with a real substance at T1, P1, turn it into an ideal gas. So this is going to be the negative of your residual property at that temperature and pressure. Then you're going to proceed with the process assuming that the substance is an ideal gas. The nice thing about ideal gases is changes in temperature and pressure are separated. Then we're going to turn that ideal gas back into a real substance. Now that's going to take us through the residual property. So to do a calculation from state 1 to state 2 for an enthalpy change, for instance, it's going to be the residual enthalpy, the negative at T1 and P1, plus the residual property positive at T2 and P2, and the changes as an ideal gas. Now for enthalpy, there is no change with enthalpy due to just pressure. So I end up with just the change in enthalpy from T1 to T2 as an ideal gas, plus those residual properties, and there should be a minus right there. For my entropy, I do need to deal with the temperature portion and the pressure portion of the entropy change. Frequently we deal with these in dimensionless forms. The reason for that is that I can tabulate them, I can write numbers in that are going to be universally acceptable no matter whether you're using SI, American Engineering, any unit system. For energy, the dimensionless form is achieved by dividing by R over T. For entropy, we only need to divide by R. Many of our equations are going to be defined in the dimensionless form. In Smith, Van Ness, and Abbott in particular, these are some of the ones that they look at. So Gibbs energy. Now Gibbs energy still seems probably a little strange. We're going to use this again really heavily in Module 14 when we look at fugacity. But Gibbs energy is an energy form, so divide by RT to make it dimensionless. And I can use just simply the fundamental relation, VdP minus HdT. I can do this for the real properties, for the ideal gas properties, or therefore for the residual properties. I'm dividing through by RT. The H was already divided by a T, so I end up with this expression here. Now, HR over RT is the derivative of this little piece here times T, or divided by T. Okay. But this expression here, and we can play around. I have not really done this with great detail here, but you can relate these going back to our derivatives and the Maxwell relations, and I can find expressions for these. Frequently they are done in terms of Z. This is convenient because equations of state are frequently written in terms of Z. And so if I do this, I can relate H to the integral of the derivative of Z with respect to temperature at constant pressure. This is integrated with respect to P divided by P. Now, the derivative is taken as at constant pressure, but it still may have P in this answer. So be sure that you don't treat this as if it's truly a constant. Whatever answer you get, divide by P, integrate with respect to P from 0 to P. Okay? There are many other forms. If I have entropy, for instance, at constant pressure, this is the expression I get. Now, it's a lot more complicated, but I have a formula that I can use. And I can use these to create a simpler definition for Gibbs energy, which would be this one. Now, in all cases, remember, Z is by definition PV over RT. In the next lesson, we're going to come back and look and see how we can apply this so that we can actually solve problems using this information.